In this video, we're going to discuss a method of what's known as constrained optimization, and the method that's used to solve such a problem is known as the Lagrange multiplier method. So let's consider an example. The function f of xy equals xy plus 5. This function has no maximum or minimum values. We can see that from looking at the graph. It looks sort of saddle-shaped. If we start here, we can go up as far as we want. Same thing over here. Here we can go down as far as we want. There is, in fact, a saddle point at the origin. We can also see from the formula that there is no maximum or minimum. If we substituted progressively larger values of x and y into the function, we could make xy plus 5 as large as we wanted. If we substituted very negative values of x and, let's say, positive values of y, we could make this as negative as we wanted. So this function by itself, it does have a saddle point at the origin. That's pretty easy to verify. But it does not have any maxima or minima. The gradient is never 0. Now suppose we want to maximize this function using only ordered pairs, only considering ordered pairs that satisfy this equation, 9x squared plus y squared equals 4. In other words, we're restricting ourselves to a particular set of ordered pairs that satisfy this equation. Well, 0, 0 would not satisfy this equation because 9 0 squared plus 0 squared is 0, so that does not equal 4. So 0, 0 is not a candidate. But let's say x was 0 and y was 2. That would then be a candidate. That satisfies this equation. However, if we substitute 0 in for x, y, 2 in for y into this equation, we would have 0 plus 5. So the idea is that even though this function does not have a maximum or minimum, if we restrict ourselves to a special set of ordered pairs that satisfy this equation, we might actually have a solution. Here's a picture of what's going on graphically. Here's our surface F. Here's the ellipse, 9x squared plus y squared equals 4. 9x squared plus y squared equals 4. Now what we're going to do is we're going to graph that ellipse in the xy plane. It's going to look like this. The function, the surface, the green surface for f, has no maxima or minima. But if we restrict ourselves to ordered pairs xy that fall along this red ellipse, and look at their images on the surface, we can see that there perhaps is a highest point on this lifted ellipse right over here. Maybe there's also a similar point over here. So what we're looking for is actually the highest point on this bent ellipse and maybe the lowest point as well. So because we're constraining the ordered pairs to satisfy this equation, we call this a constrained optimization problem. In other words, we want to solve the following problem. We want to maximize f of xy equals xy plus 5 subject to the constraint that 9x squared plus y squared equals 4. And from the graph, it appears that this does have a solution. We're going to introduce a new function. G of xy is 9x squared plus y squared. That's just the function made up of the left-hand side here. So we now can rewrite our problem as maximize f of xy equals xy plus 5, the same thing up here, subject to the constraint that g of xy equals 4. I've simply replaced this with g of xy. It's important to realize now that when we go through this problem, there are two functions. There's the function we're trying to make large, which is f, and then there's also this function g, which we call our constraint function. Each of these functions has contour diagrams. Here's the contour diagram for g. So here's the formula for g again was 9x squared plus y squared. Each contour for this function will be an ellipse. So here's the contour z equals 2. Here's the contour z equals 4, z equals 10, and so on and so forth. Now, a really important principle that we're going to use in just a moment is the fact that the gradient vector, at every point on the contour diagram will be perpendicular to the contour and point in the direction of increasing z. So for example, right here, I can see that at this point on the contour z equals 4, the z values increase if I move in that direction. So I draw my gradient vector at this point, so it's perpendicular and drawn in the direction of increasing z. Now, its length would actually be the slope of the surface in that direction, and that's hard for me to draw to scale. So the important thing I want you to notice is simply that it is perpendicular to the contour and points in the direction of increasing z. Same thing here, same thing there, same thing there. Now we can do the same thing for the function f. Its contour diagram is somewhat more complicated. Here's the contour 5.25. I'm going to draw the gradient at this point. It's got to be perpendicular to the contour through this point. I want that to be a right angle. And it has to point in the direction of increasing z. Here's z equals 5.25, 5.95, 5.6, so the gradient has to point up like that. Likewise, if I went over to this point here, the gradient has to be perpendicular to the contour, which is z equals 3.85, and it has to point in the direction of increasing z, so it has to point this way as opposed to that way. So we have two functions, they both have contour diagrams, and they both have gradient vectors that are always perpendicular and pointing in the direction of maximum increase. Now, here's the picture when we put two things together. We're trying to find the largest value of f which satisfies the constraint g of xy equals 9x squared plus y squared equals 4. So here what I've done is I've drawn all the contours for f. Those are in black. And in blue, I have that single contour, 9x squared plus y squared equals 4. Now, at every point on the contour diagram for f, we know that the gradient is perpendicular to the contour. So it would point up here, point out that way. It would point up this way. And we know the same thing is true on the single contour for g. The gradient would point in that direction. It would point in that direction, it would point in that direction. And again, that's because we were looking at the contour diagram for G by itself a couple minutes ago. Now, let's say we start at a point right here. We need to stay on this curve, this ellipse, and find the value of z for the function f, which makes f as large as possible. Now, if I'm standing at this point, the z value is 4.55. If I move in this direction, we're between the contours 4.2 and 4.55, so my z value is actually getting smaller. Now when I get to this point, my z value is back to 4.55. And as I keep moving, at this point my z value is 4.9. Then it goes up to 5.25. Then it goes up to 5.6. Then it goes a little higher than 5.6, but then it returns to 5.6. And then my z value decreases to 5.25. So it appears as I move along this ellipse, there's going to be a largest value of the function f, and it looks like it's going to be right around there. And in fact, by the symmetry of the picture, there's going to be another point down here. If I start at this point where my z value is 4.55, it goes up to 4.9, 5.6, a little higher than 5.6, but then it starts to go down again. So it appears like if we want to find the ordered pair that satisfies this formula, it appears that it's going to be right at about this point, and that there's going to be a second solution right at that point. Now here's what we need to notice at these 2 points. At this point, the gradient of the function g has to be pointed that way. Now that's not to scale. The gradient of f has to be pointed in the same direction. I'll draw it like that. The gradient of g and the gradient of f both have to be perpendicular to the contours and point in the direction of increasing output. And if we look at this carefully, we can see that the gradient of g and the gradient of f are parallel. So at the points where we're finding our maximum, at that point, the gradient of f and the gradient of g are parallel. This means they are scalar multiples of each other, which we can write as the gradient of f at x naught, y naught is lambda times the gradient of g at x naught, y naught. Lambda is just the stretching factor. We use the Greek letter lambda. It stands for Lagrange multiplier, named in honor of the Italian mathematician Joseph Louis Lagrange. So again, the point x naught, y naught, which is on the blue contour, in other words, satisfies this constraint equation, the point on this blue ellipse that makes f as large as possible appears to be right here, and also there's another point right here. There are two candidates. So we know that at either of those points, the gradient of f is parallel to the gradient of g. Here's the gradient of f written in terms of partials. Lambda times the gradient of g, written in terms of partials. We have two equations now. The partial derivative of f with respect to x has to equal lambda times the partial derivative of g with respect to x, and the partial of f with respect to y has to equal lambda times the partial of g with respect to y, which is what we have right here. So this is a system of two equations. Here's one equation, and here's a second equation, but it has three unknown quantities, x naught, y naught, and this value of lambda. So we need a third equation, and here's where we get the third equation. We use the fact that at that point, which is on the curve, g of x naught, y naught has to equal 4. So now we have three equations. Here's an equation, there's an equation, and we have a third equation. So in summary, to find the desired maximum, we must solve the system made up of the following three equations. The partial of f with respect to x at x naught, y naught equals lambda times the partial of g with respect to x at x naught, y naught. A similar statement for the partials with respect to y. And then finally, g of x naught, y naught equals 4. And this is always what we have to do for a Lagrange multiplier problem, where we're dealing with functions of two variables. It always really starts here. So you need to find 4 partial derivatives, write these three equations down, and then we're going to try to solve for x naught and y naught. Okay, so let's run through this process. The partial of f with respect to x would be y. The partial of g with respect to x would be 18x. So here I have y equals lambda times 18x. The partial of partial of f with respect to y is x. That has to equal lambda times the partial of g with respect to y, lambda times 2y. And then our third equation is that g of xy has to be 4. 9x squared plus y squared equals 4. So again, these three equations right here are just coming from these three equations that we talked about a moment ago. Now what we have to do is we have to solve this system of equations. And in general, the method is going to vary from problem to problem. In many situations, it's going to involve solving for one variable and substituting. So let's take the first two equations, which involve lambda, and solve for lambda and set the results equal to each other. So this says that lambda equals y over 18x. This equation says that lambda equals x over 2y. If we take those two and set them equal, we get y over 18x equals x over 2y. And we can cross multiply and write this as y squared equals 9x squared. After we do a little bit of simplification, you might want to just verify that. You'd have 2y squared equals 18x squared, divide each side by 2, and you'd get this. Now, one thing that's important to notice is that when we solved for lambda here, we had to divide by x. We need to reassure ourselves that x can't be 0. Well, if x was 0, then y would have to be 0. And if both x and y are 0, this equation wouldn't be satisfied. So we can rest assured that dividing by x is okay because x can't be 0 and y can't be 0 either. Okay, so now we have an equation. 9x squared plus 9x squared equals 4. We're down to one equation and one unknown. So this says that 18x squared equals 4. X squared equals 4 over 18. x equals plus or minus root 2 over 3 after you simplify. If we substitute either of these values back into y equals 9x squared and solve for y, we get y equals plus or minus root 2. Now using x and y, we find, so we actually have 4 ordered pairs here. Keep that in mind. We know that x is plus or minus root 2 over 3, y is plus or minus root 2. So there's actually 4 ordered pairs here using positive root 2 over 3, positive root 2, negative root 2 over 3, positive root 2, positive root 2 over 3, negative root 2, and finally negative root 2 over 3, negative root 2. There are actually 4 possibilities. Now, using x and y, this ordered pair and this ordered pair will give us a lambda value equals 1/6. We can get that by substituting the x and y in and solving for lambda. Lambda equals minus 1/6 is what happens when we use the other 2 ordered pairs to solve for lambda. So how do we determine which ordered pairs are solutions? The way to do that is to substitute that into the original value of f. If we substitute root 2 over 3, root 2 into f, or minus root 2 over 3 minus root 2, we get 17/3. On the other hand, if we substitute either of the other 2 ordered pairs into f, we get this is 13 over 3. Now here's what's going on in terms of our picture. One of the ordered pairs is right about here. That's where the z value is 17/3. There's another one down here in this quadrant. That's the point minus root 2 over 3 minus root 2. So 2 of the points, this point and this point, they belong in the first and third quadrants. They both make f equal to 17/3. On the other hand, there's a point down here and a point up here where the gradient of f and the gradient of g are parallel. And here's where f is made as small as possible and equal to 13/3. So to summarize the process again, if you have your constraint function g and your function that you're trying to make as large as possible f, you set up 3 equations in 3 unknowns. In this case, g of x naught y naught was 4 because that was our constraint function. Here's the function g. So in preparation for class, please consider the following problems. Solve the following constraint optimization problems. Maximize f of xy equals 4x plus 6y subject to the constraint x squared plus y squared equals 12. So in this case, g of xy would be x squared plus y squared. Maximize the function x squared plus y squared subject to the constraint xy equals 1. So in this case, g of xy would be xy.